Hello, this is a video on the overview of acids, bases, and salt, the most common solutions. By this time, you should have copied out or got this file, the overview. Plus, there is a video animation I'm going to quickly show when we do these. So you need to be able to get to that animation if you so desire. Okay, the first we'll get the easy one out of the way. Salt. What's the definition of salt? The most common definition is the general name of an ionic compound, any ionic compound. Now, with respect to acid-base reactions, which we're doing now, salts are the product of a strong acid and a strong base. The other product of a strong acid and a strong base is water. So therefore, the way in which you can explain the formation of a salt in a strong acid, strong base neutralization double replacement reaction is that the salt is made up the cation of the strong base reacting with the anion of the strong acid. Cation of the strong base and the anion of the strong acid make the salt. All salts are considered strong electrolytes, and if you haven't watched the electrolyte video, an electrolyte is a substance that, in the presence of water, breaks up into ions, and it's a negative ion and a positive ion. The negative ion is used to so electricity can conduct through it. That's where the word electrolyte comes from. So that's a salt. Now to the acid and base. This is a little bit more complicated. The first thing is actually three definitions of acids and bases: Arrhenius, Bronsted-Lowry, and Lewis. And each one is more encompassing as we go along, meaning more substances are described as a Lewis acid and base compared to an Arrhenius acid and base. And for first year, we're not going to talk too much about this. We're going to kind of, at least for now, stay in the Arrhenius definition. And maybe if we get further along, there will be other videos on Bronsted-Lowry and Lewis acids and bases. So, using the Arrhenius definition of an acid, it's a molecular compound that ionizes in water to produce H plus and anions. H plus is not called the hydrogen ion in acids and base reactions. It's called the hydronium ion. And you can see it, the symbol, as H plus or sometimes H3O plus. And H3O plus is simply an H plus and water coming together as one symbol. We use the word ionize here instead of dissociate. Dissociate means break up into its base parts. Ionize actually is a chemical reaction. The thing is, acids are not ionic compounds, but we treat them as such. Acids are actually, are actually molecular compounds, and we treat them as ionic compounds because we say they break up into H plus ions and anions. So that's not actually a dissociation, it's an ionization. That's the name you have to give it because it's a molecular compound. So that's why it's called ionizes, not dissociates. Dissociates is another word for dissolve. Some properties of acid: it tastes sour, reacts with metal to form hydrogen gas, turns litmus paper red, whatever litmus is. We'll talk about pH indicators later in a different video. And it neutralizes base. Again, we'll talk about what neutralize means in a different video. So those are some of the properties. There are two major types of acids, and the type of acid is determined by the acid substance itself, the molecular compound itself, not by how much you have in it. The two are strong acids and weak acids. Strong acids ionize 100%, whereas weak acids do not ionize 100%. Well, what are the and we'll get a little bit into that when we get the picture, when we look at these little pictures here. So which are the strong acids and which are the weak acids? There are 7 strong acids: hydrochloric acid, hydrobromic acid, hydric acid, HI I usually say because I cannot say the word, nitric acid, sulfuric acid, and then the ones that everybody forgets, chloric acid and perchloric acid. So all those are strong. Only 7 of them. So therefore, everybody else is weak. That's why it's all others. So why do we care about weak acids and strong acids? Well, they're very different in solution. So we'll look at strong acid first. Strong acids ionize 100%. What does that mean? Well, it means the HCl, remember it's a molecule, has ionized, not dissociated, has ionized into H plus and Cl1 minus. Since it's 100%, there is no more of the HCl in solution, it's just H plus and Cl minuses. So you no longer have the original molecule itself. And that's very, very important because we want to count, in this case, with acids, H pluses in solution. So when we're counting H plus, since this is, as you know, this is called a complete reaction, as it goes to completion, then we can determine how much H plus concentration there is from the HCl concentration by using stoichiometry. So if you have a strong acid, you're doing stoichiometry calculations to figure out how many H pluses we have. Whereas in a weak acid, not all the acid molecules ionize. So therefore, here's HF, this is a weak acid. So as you can see in both of them, I apologize, that there's always water in there. And we'll talk about water actually is a weak acid too. So we'll talk about that. But in this one, we have HF as a weak acid. So if it doesn't ionize 100%, what we get is we get both the ions that form when you ionize it, okay, and the original molecule, the acid molecule. So I have both of them in there. So if you look, that's a equilibrium problem. So to count H pluses, remember we have the starting material and the finishing material. Okay, so to count H pluses, we have to do equilibrium, not stoichiometry. Stoichiometry won't work because we can't say for every 1 mole of HF we get 1 mole of H plus, like we can say over here. Because that's only true if it goes to completion, which is stoichiometry. Here we have to do equilibrium. So when we count H pluses, we have to do equilibrium for weak acids. And why do we care about the concentration of H plus? Because we have a scale to keep track of H plus concentrations. It's called the pH scale. And that's all a pH scale does, is a H plus counter. That's it. Now, that's an acid. Okay. Now, with a base, the other thing I want to say is, at this level, at this time, for level 1, we only deal with strong acids. We are not going to get into equilibrium acid and bases in first year yet. That would be a completely different video, and there would be actually a couple videos on it, because it gets more complicated. Now let's go to the base side. So the erroneous definition of a base is an ionic compound, and there can be molecular compounds that dissociate, and if it's a molecular compound, it ionizes in water. Now you produce OH minuses and cations. It tastes bitter, slippery to the touch, it turns litmus paper blue, and it neutralizes acids. Again, there are two types, and basically the same idea works here. Strong bases dissociate. Now, why do we use the word dissociate? Because these are usually, as it says here with strong bases, they're usually metal hydroxide ionic compounds. And it's the metal of the group 1 and 2. So, for example, sodium hydroxide and calcium hydroxide. So they're both ionic compounds. Their base units are ions. That's why we dissociate. So therefore, they dissociate 100%. So in my bucket of sodium hydroxide, I have absolutely no sodium hydroxide. You have only Na1 plus and OH minuses. I put a little dotted line here because if it's a straight line, undotted, I don't know if that's a word, but that would indicate a chemical reaction. This is not a chemical reaction. This is simply a physical process. Okay, and with bases, I'm counting. Again, there's water in there. With bases, we count OH minuses, and since it dissociates 100%, we can use stoichiometry, because for every 1 mole of NaOH, I'm going to, in this case, get 1 mole of Na1 plus and 1 mole of OH1 minus out. Now, for the weak base, just like in the weak acid, they don't ionize 100%. Okay, not. NH3 is the most common weak base that you know, and its derivatives, meaning and chemicals that basically replace some of the H's with other chemicals. And I showed you one. It's called methylamine. Okay. Oops, that's not right. There should be an H. It should be CH3 and H2 there. I'm sorry. But it's going to act the same way. Now, technically, ammonia is not actually an erroneous base. It's actually a Bronsted-Lowry base. Blah, blah, blah. And maybe we'll talk about it. The big thing is, I didn't put it here. Big thing here is there's NH3 compounds and NH4 1 plus and OH minuses in here. So we will have all of them, even though I didn't put it in there, and I'll fix that. Here we have both the NH3 and the NH4 1 plus and OH minus in the bucket. So therefore, when we're counting this substance or this solution's OH1 minuses, we don't use stoichiometry. We use equilibrium. Therefore, we can create what is called the POH scale, which is not an H plus counter, it's an OH minus counter. Okay, so basically acids and bases there's two types, strong and weak. Strong ionize or dissociate 100%, so you use stoichiometry to find the either H plus or OH minus. Weak acids and weak bases don't ionize 100%, so it's equilibrium, because not only do you have the original substance, you have the thing it breaks up into. So it's going to have a reversible reaction go on. Okay. And again, I'll fix the not having the NH3, NH4 1 plus, and the OH minus in this, and I'll fix the NH2 problem. This should be a NH2. Okay. Thank you very much.